So now after the break, all simulations should have finished and we can have a look at the results. We again have a report, but we already looked at that, so we go to the plots. In the plot we now see a plastic behavior, so here we see the plastic deformation. And if you want to, you can also change, for example, the unit of the stress in your plot. So instead of gigapascal, take megapascal, and then click on apply. And we do not want to do that for all the result files in our result viewer. So there click on no. And now you can see that the unit has changed. If you want to save the plot, make a right click. And there you can either save an image, copy the plot to your clipboard, or save the data pairs as a text file. You can also edit the plot settings. For example, you can change the font size to, let's say, 14 and 12. And by that you make sure that all the fonts have the right size if you want to use the plot in the presentation. If you want to compare the results again, you can click on the previous result while holding the control button on your keyboard. Then you click on combine results. You can change the name, for example, by adding plastic. Click on OK. And then you have a combined result file. And if you go on plots, you can see that you have both curves in one plot. Now we want to have a look at the results. So go back to the result file, go to strain stress visualization, and then choose a time step, for example the 4th. Then click on load solution file, and there we want to load all the volume fields. And then we can see the solution. Here you again see the strain distribution in your material. And we can again look at a different volume field. For example, the plastic deformation in Y direction. If you do not want to see a certain volume field, for example of the fibers, you can deactivate it in this menu. And then you only see the polymer. After finishing the simulation of the plastic behavior, we now want to go on and look at damage and failure. And to do that, we first need to find a damage law for the polymer. So we go to Settings, click on Edit Material Database, and then we add a new material law. I will call it Polymer Damage, and then click on Add. We only want mechanical properties, so we only activate that checkbox. And then we go to this tab. And then we have to add a material law, and you can call it damage again. You could make several laws for one material, for example at different temperatures. So here we could now just define a Young's modulus and a Poisson ratio or a plasticity model such as perfect plasticity, define the initial yield stress. But if you have a more complex material law like exponential hardening, or what we need in our case, exponential damage, there are many more parameters you need to know, and you usually do not find them in a datasheet. But what you can do is, you can fit them to a measurement, and to that, you go to the Measurement tab, then activate Save a Measurement, and here you can now, for example, load a measurement from a text file. You can copy data pairs into this table, or you can add them manually, and that is what we will do now. First, we need to adjust the number of rows to 9, and then just type them into the table with me. It's first, of course, 0 and 0, then it's 0.3 and 0.0, and be careful because all the stresses are in gigapascal, not in megapascal, as on many polymer datasheets. Now we go on with 0.9 and 0.027. Then we have 1.5 and 0.04. Then we have 2.1 and 0.047. 2.7 and 0.048, 3.3, and 0.044, 3.9, and 0.037, 4.5, and 0.029. You can then click on Update Graph, and then you see a preview of the curve of this experiment. And then we go to fit law parameters. First of all, you have to choose the law you want to use for fitting. There you have plasticity laws and exponential damage, and that is what we are going to use. Then I always suggest that you click on Keep Initial Stiffness. That makes sure that the estimated stiffness is used and that the fitting routine does not fit unrealistic stiffness values. If you have a stiffness in your datasheet, I suggest that you take that stiffness as initial stiffness. You can do that by activate set initial parameters, because sometimes when the data points in your curve are far apart, then the estimate of the Young's modulus is not correct. You can also adjust the other initial parameters, and if you want to look at the curve, you can click on plot initial curves, and then you see the fitted law with those initial parameters. And that does not look that close. So we are going to adjust the initial parameters. Change the damage evolution to 1 and the damage hardening modulus to 300. And then click again on plot initial curves. Okay, so now the curves are still not at the same stress level, but they have the same shape, and that's a good starting point. To be honest, I cheated a little bit because I tried out which parameters give us a quick fitting run in advance. So now hit Run Parameter Fitting. That takes a couple of minutes, because for each parameter combination, Geodict runs a simulation on one voxel and thereby optimizes the parameter combinations towards the right curve. Now the fitting is finished, and you can see that our fitted law is almost identical to the curve from the experiment. And to transfer the values from the fitted law to our material law in a material database, click on Set Parameters to Law. And then you can see that you have them here in the Law tab. And don't forget to click on Save Database, otherwise your data is lost. Now we have a material law for our polymer that also includes damage, and we can go back to the mechanical simulation. So go back to ElastoDict, make sure that FEMATH LD is chosen and click on Edit. And now we have to choose our new law for the polymer. Polymer damage, and click OK. Here in this drop-down menu you can see that we only have one material law, the damage law, and we activate this damage model. For the carbon fibers we use the failure law, and you can see here that the longitudinal stress and the transversal stress for failure are 4.1 gigapascal. This law is already included in the Geodict material database, and we can use it for the simulation. Now we go to the macroscopic load case. And we want to start with a tensile test in x direction. So we change the load direction to x. As the magnitude, we enter 2.5 in 10 steps, and then we click Apply. For the boundary conditions, we can again take periodic boundary conditions because we are applying the load in fiber direction. In the Solver tab, we leave everything as it is, but make sure that downsampling is not activated. We will not use downsampling for this simulation. Then we change the file name. I call it fail dem x for x direction. Then we go to the Output tab. And there, under Deformed Geometry, we activate white volume fields for deformed geometry. We do that because we want to save a video later on, and for that we need those fields. And then I also want to save the stress in x direction, so also activate that. And then click on OK. And then click Run. Because we do not use downsampling, the simulation might take a little bit longer, but it's still going to be very quick, and we are now going to wait for the solver to finish. Now the simulation has finished, and we're going to look at the plots. And here you can see that failure occurs at around 1.75%. Of course, failure can just set in at one of those points, and their position is defined by the size of the steps, in our case 2%. For a more accurate result, you can just decrease the step size. What I always do then is I count the number of steps until something interesting happens, in this case failure. And it's 1, 2, 3, 4, 5, 6, 7 steps. Then I go to strain stress visualization, and I take the 1, 2, 3, 4, 5, 6, 7th load step, and I load the solution file. And for now we want to load all the volume fields. Okay, then minimize the result viewer, and here we have the results. There's now displayed the strain again. First we deactivate the structure. And then under volume field we load the stress in X direction to see especially the load in the fibers. So here you can see that the fibers take up almost all the load. The stress is 4 gigapascal, which of course makes sense because we are in the load step before failure. The polymer takes up almost no load compared to the fibers. Then we can also look at failure in the fibers. And failure is a value between 1 and 0, and 1 means that a voxel has failed. So here you can see that there is no failure. Makes also sense because we are on the load step before failure, and in this material law failure occurs suddenly. Then we can also look at the damage in the polymer. And here you can see that although everything is red, the damage is not that high yet. It's only 0.26. So to get a better impression of the damage distribution in the polymer, we are going to adjust the color map. And you can do that by clicking on Edit. Then you change to Manual. And then you can adjust this value window and make it narrower. You can see that it's a bit better, but not as good as we wanted. So now you can see a distribution. Of course, the value range is now not that high, but if you want to get an impression of the distribution, that's how you can do it. Okay, so now we want to look at the load step after failure occurred. So we go back to the plot and have a look. That's the 8th load step, and we change to that. That's time step 4, and click on load. Again, click load all the volume fields. And then here you can see the next load step. We again go to the failure and the fibers. And here you can see that there is now failure in the fibers, and we now want to clip this volume field. So in the drop down menu clip, you choose failure. And then when you move this slider, you can see that the failure in the fibers is almost everywhere at 1 or almost 1. So all the fibers have failed. And they cannot carry any load anymore. And that you can see when you look at the stresses in X direction. So we move back the slider and go on stress in X direction. And there you can see that all the fibers are blue. That means that they carry no load at all, and the polymer does all the work now. So now we go back to the result viewer and click on load structure to make sure that the structure is loaded. And we also want the structure to be visible, so click on yes. And now we are going to make a video, so go to create videos and then click on edit parameters. And here first you have to select the invisible material ID. We want to see our material, so choose something like 3, which is not included in the simulation. We want to show the stress field, so leave that activated. Now we have to give the minimal value for the stress and the maximum value for the stress, and we saw that the maximum was around 4 gigapascal, so add 4. Then we have to select the clipping direction to see half structure and half volume field, so it's separated in the middle. And there we choose the Y direction. Then you can choose the font size and the video duration. We leave that now as it is in the default settings and click on OK. And then click on Create Videos. Click on OK. There's something with the scale bar, so just click on Yes. And now Geodict saves an image of each time step and then generates a video from those images. Okay, now the video generation has finished. Click on OK. And then we want to look at the video. And the video lies in the result folder. So make a right click on the project folder, go to Open Result folder, open the folder of our last simulation. And there's a file called largedeformation.mp4, and then open that file. Okay, so when you look at the video, you can see that the load, especially in the fibers, increases. In this case, it's per default always the von Mises stress. But you can see that the load increases gradually, and then after the failure stress is reached, the fibers do not carry any load anymore. Now we go back to the result viewer and load the structure again. We minimize it. Go to Elastodict and click on Edit. We again activate the damage and the failure law, and then we go to macroscopic load case. Now we want to simulate a tensile test in Y direction, because in Y direction the damage in the polymer will be a lot more important and we want to see that, so choose Y direction. Here the magnitude we change to 5% and the number of steps to 20, and then click Apply. And then we choose Mixed Boundary Conditions, as we already had to before when we were simulating transfers to the fiber direction. Then go to Solver. We increase the tolerance to 0.005 to make sure that the simulation run will finish within this workshop. Of course, you should not do that if you need accurate results, but for the workshop it will do. The rest we leave as it is. Make sure that downsampling is not activated. Then we go to Output. We do not have to write the volume fields for deformed geometry because we are not going to save a video. And we change the stress from X to the Y direction. Then we have to change the file name and replace the X by Y. And we click OK. And then we click Run. And then we wait for our last solver run in this workshop to finish. So now the simulation has finished and we are going to look at the plots. And here you can see that after an increase and a little plateau, the stress decreases again, and that is caused by the damage. And we are going to look at the 1, 2, 3, 4, 5, 6 time step. And we load the solution file. Again, we load all the volume fields. Deactivate the structure. And now we see the strain distribution, and you can see that the strain is highest where fibers are close together. And we change that to the damage. Damage is again a number between 0 and 1, while 1 means that the voxel cannot carry any load anymore. And you can see that the damage is highest where the stresses were highest. They are almost like paths of damage going through the structure. Then go back to the result viewer and load the next time step 2. And click on load, and again all the volume fields. And here we now see the strain again. We go back to the damage, and we see that the damage is more pronounced, and also that it's approaching 1 in many voxels, and you can see that there are paths of failure like cracks going to the entire specimen, and in a tensile test this specimen definitely would have failed up to now. Now we are at the end of our workshop, and I really thank you for joining. And if you have any questions on mechanical simulation, composites, geodetic, please feel free to contact me. And for the rest of the user meeting, I wish you a lot of interesting more insights, new ideas and inspirations for your own digital material R&D.